Okay, so in this lecture, in this lecture series, I will introduce you a proof of Picard's little theorem, which is contained in the book Classical Complex Analysis. So the proof involves some basic complex analysis techniques, Cauchy's estimate, Liouville theorem, maximum mergers principle, Schwartz lemma, Roche theorem, the Riemann theorem, and the Casorati-Weierstrass theorem. So in this lecture, I won't go through Cauchy's estimate, Liouville theorem, and the Maxwell's mergers principle. You can find it in basically the classical complex analysis course. So I will start with proving the Schwartz lemma. So start with the Schwartz lemma. So let Fd be a bounded analytic function in the disk. So I will use this notation for the disk, which means that the open disk centered at 0 with radius big R that satisfies the condition f at 0 equals 0. Okay, so f at the origin in the complex plane is 0. Then we have f prime at 0, where it's taking the complex derivative. Because f is analytic, so f is homomorphic, so you're allowed to take the complex derivative. And so I will tell you what this m later. So the modulus of fz is less than or equal to m over r of the modulus of z for z in z in the disk with radius r, open disk with radius r, where this m is defined as. So I use this symbol as being defined as the slope, or maybe you can use f equal to the supremum over the modulus of fz z in disk with radius r. Okay, so m is the supremum of the modulus fz. So furthermore, if so, this is like a upper bound for the derivative at 0. So if the the next condition is that if the upper bound is achieved, so if f prime at 0 is equal to this upper bound m over big R, or so either of these conditions is satisfied, or the modulus of FD is achieved is equal to this M over R modulus of V. Is if holes, oh sorry, so if the modulus of f prime 0 equal to M over R, or the modulus of Fz is equal to M over R modulus of Z, if this relation holds at even one point in addition to Z equal to 0, then the function is a dilation. So this means that Fz is equal to e to the I alpha M over R Z for some alpha E V. Okay, so I'll explain what I mean by this sentence here. So if either these, so there's two conditions. Okay, so there's like two different conditions. So one condition is f prime 0, the modulus of f prime 0 is equal to M over R. Okay, and another condition is the modulus of Fz is equal to M over Rz for one more extra point other than the point z equal to 0. So if either of these two conditions holds, so they may not hold at both times, but if either of these two conditions are satisfied, then we say that this function is a dilation. Okay, so let's begin to prove this. So proof. So first, because this f is analytic, we can have the we know that this function has a power C expansion at the origin, because this disk contains the origin. Okay, so and yeah, so so we consider the power power 3 expansion of the origin. So since since f of 0 is equal to 0, so we know that the constant term vanishes. So let's start with the first term. Okay, so here the notation is a little bit awkward. So usually there will be like 2 factorial, 3 factorial stuff. So here we just ignore it. So imagine that the factorial is kind of contained in the coefficient. Okay, so we define another function. Let the function g of z to be the function f of z over z. Okay, so take another function g to be fz over z, which is just a1 plus a2z plus maybe I should write a n z to the nth power, and here I can write a n to the z to the n minus 1. Okay. So this is your g of z. Okay. So okay. So the thing is that originally this g of z because I defined this gz to be f of z over z. But the thing is that this gz originally is not defined at 0. Okay, it's not defined at 0. So what we do here is that we can use the because this 0 is a removable singularity for this function gz. So so we just cover this gz by whatever this guy a1 for g of 0. Okay, so g of 0 is just a1. Okay. Okay, so now what we do is that that z0 to be d prime 0r. So for the d prime, I mean the punctured disk 0r. So the origin is punctured out. Okay. So maybe I can write okay. So sorry, this modulus cannot be equal to 0. Okay. So so then choose this smaller radius r such that this z naught is in d0r. Okay, so pick a bigger radius such that this point is contained in the disk with radius r. Okay, and so then okay, so then we apply the maximum modulus principle to this on this the closure of the disk. Okay, so because to apply them, okay, so I'll explain why how the maximum modulus principle work. So we have modulus of f of z naught over z naught. Okay, so this is what g of z naught is, the modulus of g of z naught. Okay, so this is less than equal to, of course it is less than equal to the maximum of the modulus of gz for z in the closed disk of radius r, right? It's less than equal to the maximum. So so basically, so here we know the maximum. So the maximum is okay. So basically, the maximum exists because this domain is a compact domain. So so for any compact domain, it contains all the limit points, right? So basically, we can just say that the supremum of this function gz is at x maximum, and the supremum it exists. Yeah, and the supremum by this compactness and this function modulus of gz being continuous, we know that the supremum is achieved on the closed disk. All right, so let's see, which is equal to the maximum of modulus of gz z in C0R. Okay. So what I mean by C0R is the boundary of the disk with radius r. Basically the circle center at 0 with radius r. Yeah, so if the, yeah, so basically, so if the maximum is achieved at the interior, then it will violate the maximum modulus principle. So basically, the maximum must be achieved over the boundary. So therefore, yeah, so therefore the maximum must be achieved over the boundary. Okay. So this is equal to the maximum of this modulus of fz over z, z in C0R. Okay. And remember that we have this. What do we have? Sorry. Okay. So we know that this M is the supremum of this Fz for this big disk, right? Supremum. Yeah. Yeah. So and then okay. So yeah. So here is the because basically like. So if you have this okay, so since this Fz over Z, so which is modulus of Fz over modulus of Z, so this is less than or equal to this M over. So since this modulus of this z is, so we are taking the z to be, oh, okay. So here this modulus of z is just r, right? So, and this r we know that is less than this big R, right? So here we have that 1 over modulus of z, which is 1 over r, is bigger than 1 over r. Okay, so this is like fz over modulus of z over this small r here. Okay, so we have that. Okay, so yeah, so here we have that. So we know that this we know that this modulus of fz over z is less than or equal to the big M over R. So therefore, so there is a theorem saying that the maximum of a function is the same thing as yeah. So yeah, okay. So this is like an upper bound, right? Yeah. So this is like an upper bound for that. So by definition, the maximum is also one of the function values. Yeah. So this is must be less than or equal to the upper bound. Okay, so we have that. Oh shoot, sorry, I messed up again. So this should be small r. Okay, so yeah. Yeah. Okay. A little bit bad here. Okay. Yeah. So yeah. Nothing. Okay. So just ignore everything. Okay. So less than or equal to this M over small r. All right. So what we have next is that. Okay. So since this r is just anything that's any radius that is bigger than the radius of z, bigger than the modulus of z. So that we have that this let's see less than or equal to this M over big R, right? So if we let this R approach to this big R, we get this equality. Okay. Okay. So okay. Okay. So now we prove this one, right? So we will prove this equality for any because this V naught is in any so okay, so here, right? So for any z, so this V naught is arbitrary for the puncture disk of radius r. If we pick this, oh yeah, so if we pick this z to be the center, right? So we know the equality holds.
Okay.
Okay. Yeah. Thanks for coming. Okay. Yeah. So this is purely satisfied. Okay. So yeah. So if z is not at the origin, then this one is true. All right. So what's next? Okay. All right. So we still need to show this inequality, right? So yeah. So the step will be similar for this inequality, but instead of using well, we will use the Cauchy's estimate to show this inequality. So sorry, let me yeah, I always forget this. Let me just recall what. Let me just see what is the Cauchy estimate. So okay, so the yeah. Okay. So the thing for Cauchy's estimate is that so for Cauchy estimate, there's a radius. Okay, so yeah, I assume that you know Cauchy estimate. Okay, so for Cauchy estimate, you cannot pick the radius to be the big R. Okay, that's not possible. So what we do is that we pick this small r, right? So f prime 0 is less than equal to this m over this small r. Okay, and then where this r is that. So basically the idea is that we pick smaller disk that the closure of that small disk is contained in this bigger disk. Okay, so we can apply the Cauchy's estimate on the small disk. Okay, so letting r goes to r, we have so we have the equality. Okay. All right. So the first part is being proved now. Okay. So what about the second part? Okay. So for the second part, so if the maximum is being achieved, okay. Oh, sorry, not the maximum, but if these numbers are achieved, so what happened? So okay, so so if the modulus of f prime 0 is equal to this m over r, then then we know that this f prime z attains its local minimum. At 0, right? So if the so this is like an upper bound, right? So this is like a upper bound for wait. So sorry, let me oh. Oh, okay. Wait. F prime y. Oh. y at times its local maximum.